Hello everyone, I'm Sebastian Y and this is Foundations of Economics. In this video I'm going to show you how to maximize profit for a monopoly, algebraically, and on a graph. Just like what we did with perfect competition, we are now moving into a little bit more complex world where we can select any quantity at all, not just integers. If it's helpful, think of the good that we're selling as a liquid which we can measure to any quantity. Some of the equations that I give you here do require calculus to derive, and I'm going to leave those derivations for a later course. For now, I'm just going to give you the equations, and we'll talk about their interpretation. For an example, consider a market with the demand function QD equals 240 minus 2p. A monopoly operates in this market. Before we go on, the first thing we need to do is solve for the inverse demand function. The inverse demand function is the exact same thing as the demand function that we see in front of us, except that we solve it for p instead of q. Let's see how to do that in this example. First thing I'm going to do is add 2p to both sides, so I'm going to get q plus 2p equals 240. When I write the inverse demand function, I do generally drop the superscript d on the q. I'm then going to subtract q from both sides to get 2p equals 240 minus q, and then I'm going to divide both sides by p to get p equals 120 minus q over 2. Remember that when we divide an equation by 2, we need to divide everything by 2. A common mistake I see here is people writing something like 120 minus q and forgetting to divide the q by 2 as well. Remember that our goal is to maximize profit. We're going to increase quantity if marginal revenue is greater than marginal cost. We're going to decrease quantity if marginal revenue is less than marginal cost. And so that means we must have found the profit maximizing quantity if marginal revenue equals marginal cost. To do this algebraically, we're going to need to find functions for the marginal revenue and marginal cost as functions of q and solve those for q. For the marginal revenue function, there's a simple trick we can use to figure this out. We take the inverse demand function and we simply double the slope. So we're going to get marginal revenue equals 120 minus q over 2 times 2, and so those 2's are just going to cancel in this example. So we just get marginal revenue is 120 minus q. Suppose that our marginal cost is given by mc equals q over 2. I will simply give you the marginal cost function for one of these problems. Formally, we would find both of these with calculus, but again, I'm just going to give these to you in this course. To figure out the profit maximizing quantity, we're going to set marginal revenue equal to marginal cost, and then we'll solve for q. I'll add q to both sides, and that's going to give me 120 equals q plus q over 2. Q is equal to 2 over 2, so that we can add those up, and we can get 3q over 2. Now we just multiply both sides by 2/3, so we get q equals 120 times 2/3. And that's going to give us a monopoly quantity, and I'm going to denote that with a superscript m, equals 80. Once we know the quantity, we can then use the inverse demand function to figure out the price. The inverse demand function in our example was p equals 120 minus q over 2. That means our profit maximizing monopoly price is going to be 120 minus 80 over 2. So we're going to get 120 minus 40, which equals 80. The fact that the profit maximizing quantity and price were equal in our example is pure coincidence and definitely does not have to be the case all the time. Let's take a look at our example graphically. Remember that our demand function was QD equals 240 minus 2p with an inverse demand function of 120 minus q over 2, a marginal revenue function of 120 minus q, and a marginal cost function of q over 2. As always, I'm going to graph the demand function in blue. I can use either the regular demand function or the inverse demand function here. They are the exact same line. From the regular demand function, I can see the quantity intercept is 240, and from the inverse demand function, I can see that the price intercept is 120, and then I can just draw a line in between those. For our marginal revenue function, that starts at the same point on the price axis as the demand, 120, but you can see that it has double the slope. And so its quantity intercept is going to be at half the quantity of the demand function, which of course is 120. I'll then go ahead and draw the line. Remember from our previous example that marginal revenue can actually go into the negatives. And so even though I have stopped the line here, it actually does keep going below the axis. For the marginal cost, we have Q over 2. If I plug 0 into that, we're going to get 0. That definitely does not have to be the case, though. Sometimes you will get a marginal cost curve with a positive intercept on the price axis. And it has a slope of 1/2, so for every 20 we go over, we go up by 10. I'm going to draw that in. Algebraically, we found the profit maximizing quantity by finding the quantity where marginal revenue equals marginal cost. On the graph, we can see that happens right here at a quantity of 80, which is exactly what we found before. It's going to give us our monopoly quantity of 80. And then we plugged that 80 into our inverse demand function to get the price. On the graph, all we need to do here is find the price that corresponds with our quantity of 80 along our demand curve. We can see that that also equals 80. Again, that's completely coincidental to this problem. A few things we can see from this graph. First of all, for any given quantity, the marginal revenue is lower than the price. This is because when we increase quantity, price has to come down, so marginal revenue is always lower than the current price. At the profit maximizing point, marginal cost equals marginal revenue, and since marginal revenue is lower than price, marginal cost is also lower than the price. To determine the profit, we are going to use pi equals total revenue minus total cost. I can rewrite this as price times quantity minus average total cost times quantity, and then factor out the Q to get pi equals Q times price minus average total cost. Suppose that in our example, the average total cost is 800 over Q plus Q over 4. At our profit maximizing quantity of 80, the average total cost is 800 over 80 plus 80 over 4. This comes out to 10 plus 20, which is 30. If we find that on the graph, we can see that happens right here. And I'm just going to sketch in our average total cost curve. It's not going to be perfect, but we need to have two things happen. It crosses through that point of 80 and 30, and also its lowest point is where it crosses the MC. It looks something like this. Using our definition of profit, quantity times price minus average total cost, on the graph, that is going to be a rectangle with a base of our quantity of 80 and a height of price minus average total cost. So we're going to find our price here. We're going to come down to where our average total cost sits. That's going to be right here at 30. And then we'll come across at our quantity of 80. And that's going to be our total profit. To calculate that, we're going to take quantity of 80 times a price of 80 minus an average total cost of 30. And that's going to come out to 4,000. Note that this is a positive profit, but in the long run, this profit will persist, unlike in perfect competition, because high barriers to entry are going to prevent other firms from entering this market. For example, our firm might have a patent on its good. This is the basic process to maximize profit for monopolies. In the next video, we are going to talk about the efficiency of monopolies and what the government can do to improve that efficiency.